Okay, so we're recording. So all of the lessons I record, I put onto YouTube, so anybody can get it on their phone if they want to see it again. I also will be sending the presentation to your teachers from Michael from Challenge Aid, and that means that they can use it and show you it if you want it. Okay, so let's go. So this is about the periodic table and families of elements, and you may know much about the periodic table, but let's start from basics. So here we go. So my lesson today is this. It's about this. Now we're going to do today the periodic table, and we're going to do the families of elements. And if we move fast, we will do periodicity, which is the change across a period. But today we will probably not do that. This is the syllabus. It is huge. Don't write anything down. Do not write this down. It's silly. If you look at KCSE, they have massive syllabuses. We can cover most of this today and next week. Okay, almost all of it we can cover today and next week. Don't bother looking at it, it's too small. Okay, I'm just showing you it's huge. So here, hello Dandora, are you okay? I'm not expecting it. I'm not expecting you in that last slide. This one, I am not expecting you to read that. Okay, I'm just saying there it is. Okay, you do not need to read it. Here is a modern periodic table. The modern periodic table is shaped like this. It has another two periods down underneath, which actually fit into these gaps here. And you might be very familiar with this kind of periodic table. Group 1, Group 2, the transition metals, and in some periodic tables it calls this Group 1, the first one on the left, then Group 2, and then if you look on this one it says 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for the periodic tables, and then the boron and aluminium group is number 13, then carbon is 14, nitrogen 15, oxygen 16, and so on. Okay, do not write anything down. Sometimes the periodic table goes 1, 2, and then the transition metals, and then 3, 4, 5, 6, 7, 8, or 0 for the noble gases. Periodic tables come in many different shapes. Here's a different one. You may never have seen this. I'm just showing you for interest. Here it is. You go, gosh, I've never seen this. Here's another one. Ugh. This is a very difficult periodic table to understand. But if you look at it, it starts in the middle with hydrogen, and then helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on. It goes in a spiral. Now, the spiral is quite useful. Here's another one. This is sort of like a galaxy. Here's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on. There are many different ways of doing it. Here's a really strange one. This is based on the amount of chemicals in the Earth's crust. Not much use. Here is one with Dmitry Mendeleev, the Russian chemist who put this together behind it. But let's stick with a really easy one in just a minute. This is a typical question that comes up in KCSE examinations. So they show you a bit of periodic table, they use some letters, they say these are not their original symbols, and then they ask you questions. What is the formula between C and A? Which element has the same electronic structure as F and A? Element Q has an atomic number of 15, put it on, etc., etc. Okay, so that's a typical question, and that is the sort of question we will be able to do by the end of next week without any question at all. But back to the periodic table. So here is the periodic table. Just look at it for a moment. Just remind yourself. In this one, they have a code which shows the alkali metals, group 1, are here. Notice that they show hydrogen a different color from the rest of group 1. Then they have group 2 in orange, and the groups you really need to know about are group 1, group 2, group 7, the halogens, and group 0 or 8, the noble gases. Okay, so that's what we're going to look at. But you first need to know how the periodic table is structured. I'm just going to show you something. When Dmitry Mendeleev started on his periodic table, there were many elements which they didn't know about. They had not been discovered. They knew about the masses, the weights of some of the elements, but that was all the information they had about many of them. So what he did was he put them in order of atomic weight. And then he did something clever. And what I'm going to do is I'm going to just write on the board behind me, I hope you'll be able to see it, some of the elements of the periodic table, and then I'm going to explain what happens next. So I hope you can see this here. So I'm going to start with hydrogen, because that's the first element. This may seem to you like a silly thing to do. All I'm doing is putting them in a general order. I'm bored. It's just a long list of all the elements. Hydrogen, helium, lithium, beryllium, boron, carbon. You don't need to do this at all. But what Dmitry Mendeleev did was this. He went, hang on. I'm going to look for elements that I recognize. And he recognized lithium. And he knew sodium. So he found sodium. And he knew potassium. Okay? And then he looked at some other elements which he knew. So maybe he looked at fluorine and chlorine and bromine. And what he noticed was the patterns repeated. And all he did then was to put the same elements into columns. So lithium above sodium, above potassium, and so on. Okay, so he just moved on. Oh, I've missed out Ne. Neon comes in here before sodium. So he came up with the idea of a periodic table, periodic happening every so often, like January, February, March, April, January, February, March, April, January, on and on. Okay, same with this. Group 1, Group 1, Group 1, Group 1, and so on. Get the idea? So he was saying, okay, I'm going to stack them up. So what he did was to stack them up. So all of group 1 turned up in one place, all of group 2, all of etc., etc. And that's how he built it. Now, what's important for you to know is how the string of elements, because he just wrote them in a long line, how that string is organized in the periodic table. These are things you need to know. So I'm going back to share my other screen. So here we go. Excuse me. So here they are. So all I've done is I've taken lithium, and I've taken sodium, I've taken potassium, rubidium, cesium, francium, put them all in one column, okay? And then I've put in fluorine, chlorine, bromine, and so on. They're all just in one column. And surprisingly, the periodic table came together. Now, there were many elements he didn't know anything about. He didn't know anything about, for instance, they didn't know anything about what we call germanium. He knew about carbon and silicon, but he said there's a gap. Germanium, there's an element there that hasn't been discovered. That was important. To us, not so important. So what do you need to know? This is what students need to actually know. Firstly, the periodic table is in order of atomic number. Maybe you know that already. That's great. They are in order of atomic number. Similar elements in columns or groups. And the point about the groups is that every element in a group has similar chemical properties and a gradation. That means a change in physical properties. We will see that with group 1 in just a minute. So there are 3 things you need to know. That all the elements are in atomic number order, that the groups are the columns, and that the groups contain similar elements. They have very similar chemical properties and a gradation in the physical properties. You also need to know that the rows are called periods because they that January thing. So we come to group 1, 2, 3, 4, 5, 6, 7, 0, and then 1, and so on. There are about 120 elements. Once they asked in the examination, they said, how many elements are there? About 10, about 50, about 100, about 200. Well, there are about 120. So about 100 was the closest. That's all. Most of them are metals. If you look at the periodic table, almost none of them are non-metals. Okay, the vast majority are metals. There are some metalloids and non-metals. You don't have to worry about the metalloids. Okay. So the first group we have to know about is group 1. And you need to know quite a lot about group 1, group 2, group 7, and the noble gases, group 8 or 0. So these are the ones that we need to concentrate on. And we're going to look at each one of these a little bit just now. Okay, so let's have a look at group 1. The first thing is you need to know about the electronic arrangement. Okay, the electronic arrangement for each element up to around about element 40. Sorry, element 20, mass of 40. And I'll show you that in just a minute. You need to know the outermost electrons. You have to be able to work it out. And you have to be able to work out the electron arrangement for the whole of the sodium period. That's the row which has sodium at the start. Okay, so you need to be able to work out electronic arrangement. So I'm going to stop sharing just for a moment. Okay, so what I need to know is I am happy, this is for you, I am happy working out electron arrangement. I am not happy about working out electronic arrangement. So Matharia saying, yes, Glory. Hey, Glory. Chemistry. Ah, got you. Yeah, good, excellent. Silver Spring. Hello, Silver Spring. How nice to see you. Is this fine, electron arrangement? Yes. Dandora, is electron arrangement okay? Excellent. Good. Okay, that's great. So you can put your hand down again. So I'm going to go back to this. Okay, so electron arrangements are just normally we'd put a full stop between the numbers. So we're going to have a little test just to make sure you can. So we would just use them as shells or energy levels. These are words which mean the same thing. And you have to use these to predict the electron arrangements of the ions. Okay, so we have an assumption that we can assume we know what the ion will be. So sodium 281 will lose one electron, become positive, and become 28. Okay, so here's some now. What I'd like you to do is to have a go at these just briefly, just so you're doing some work. Just work out the electron arrangement of magnesium, calcium, argon, potassium atoms, and the Mg2+ ion and the F- ion. Okay, just have a go. Just write them down, and I'll give you all the answers in just a minute. Just have like 2 minutes to write these down. The atomic numbers are there. That tells you the number of protons, which is the same as the number of electrons. Just have a go. I'm sure you can do it. That's great. I just want to wake your brains up. Magnesium, atomic number 12, chlorine, 17, argon, 18, potassium, 19. Magnesium 2+, atomic number 12. F-, fluorine to start with, has an atomic number of 9. The atomic number being the number of protons, not the number of electrons. In an atom, they are the same. Okay, has everybody done that? Everybody done that? I'll just have a quick look at Dandora, who want me to have a look at theirs. Come on. Hang on. Oh, something funny happening here. Oh, I can't expand your... Why can't I expand your picture? Let me just stop sharing just for a moment. Let me see. Excellent. Well done. Oh, hang on. Wait a minute. There was one. Hang on. Sorry. Can you show me that again? Yes. Good. Excellent. Well done. Good. Okay. So here we are. Here are the questions and here are the answers. Ready? Mark your own. See how you get on. Bing. There. Magnesium, 282. Chlorine, 287. Argon, 288. Potassium, 2881. Magnesium, well, when it is magnesium on its own at the top, 282. So to fill it, to have a full outermost shell, it will lose the 2 outermost electrons. And so it will become 28. Fluorine, normally just 27, will pick up 1 electron and become 28. Magnesium 2+ and fluorine minus have the same electronic configuration or electron arrangement. The word for that is isoelectric. Isoelectric, meaning the same electron arrangement. Has anybody got any questions about that? Anybody got any questions about that? Okay. So the next thing that you have to be able to do is to work out formulas. So let us say we have 2 elements and we are trying to find out the formula. Just in case you're not sure about this, I'm sure most people are confident on this. But let's say I have two elements and they are 2, 8, 8, 2, and we'll call that A, and B is 2, 8, 7. Now, if you look at these two, what you've got to do is to work out what they're going to do to lose or gain electrons, and then what their formula will be together. So A, 2, 8, 8, 2, it will lose 2 electrons. Okay, so it will lose 2 electrons. This 2, 8, 7 will gain 1 electron. Now, the point about this is that valency is just the number of electrons it gains or loses. So A has a valency of 2, and B has a valency of 1. And all we have to do then is to cross these over. So it becomes A, 1, B, 2. That's how we do it. That's how we work out formulas. Okay, so just remember how to do that. It's really simple. Very, very simple. I hope you can see that there's not too much reflection. We just swap over their valencies. And that means that if they give you a formula, you can just undo that. You can go, okay, it's A, B2. And so A has got a valency of 2 and B has got a valency of 1. That's important. They often ask a question like that. Okay, let's have a look at the groups. So here we are. Okay, so the first group is group 1. And what I'm going to do is I'm going to show you an old video. It is an old video, but it is quite a good video in that it shows us quite a lot of things about this particular. Hang on, I'm just going to share it in a different way. Where is it? Okay, this is a video about lithium, sodium, potassium, rubidium, cesium, and it shows us first the elements being cut. These are pieces of, this is a piece of lithium, and you can see that it is quite easy to cut with a knife. And when it is cut, it is shiny. But you will also know that it goes darker quite quickly. It goes darker quite quickly. When you scrape it, it will go shiny again. So in a minute, they will get the spatula and just show you that underneath the dark, oh, hello, I don't want that to happen. So here it is, it's cut, and they are going to, it tarnishes, it reacts with the air. So it's still shiny underneath. Then it's kept under oil. This is a piece of sodium, and it's difficult to tell, but it's actually cutting easier. So sodium is softer. Okay, it is a much softer element. And this is potassium. Potassium is really soft. You can squash potassium with your fingers, and it changes color really fast. The lithium lost its shininess quite slowly, the potassium very quickly. Now they're going to put the elements into water. And I want you just to stop just for a minute and spot some things that are happening. So this is lithium, and it floats on water. Okay, so the first thing is that it floats on water. That's the first thing. Okay, the second thing is that it once it's floating, it moves around, and it moves around because it produces hydrogen and heat. So let's see it. Here it is. It's moving around. It's producing a gas. This is sodium. Sodium goes a little bit faster and it melts. That's why it's round. Sometimes it actually catches fire. Now we're going to see the equation. This is Na plus H2O gives half a hydrogen and sodium hydroxide. I'll write that out for you in a minute. This is potassium. Potassium is more reactive, so it catches fire straight away, and sometimes it blows up and makes a noise. I'm just going to turn on the sound for this. This is rubidium. So this is obviously much more reactive. Here comes cesium. Oops. That's a mistake. you really don't want that to happen in your experiment. Okay, so let's just put down the things which are most important. So group 1 elements. Firstly, they all float on water. That means they're not very dense. They all float on water. The second thing is they are quite easy to cut. You can cut them very easily. They're quite soft. Both of those are because they have metallic bonding. That is, the atoms are quite big. They lose one electron. That electron moves around, and they are not very well attracted to each other. What they call tarnish. That means go darker in air because they react with it. So they're all kept under oil. When you put them on water, they react in a very similar way. And I'm going to write the equation here on the board. So I will write it for sodium, but it's the same for each one of them. So I have Na plus H2O. Sodium is more reactive than hydrogen, so it displaces the hydrogen. So the sodium takes the place of hydrogen, one of the hydrogens, and kicks out the other hydrogen. Because, please mute, because hydrogen goes around in pairs, that has to do. Now, if we're going to balance the equation, sorry, Wamwini, I'm just going to mute you. Somebody else, guys? Could somebody? Thank you. Could somebody just mute, please? Thank you. So here's the equation. Guys, we need to have it. We need to have it muted.
Team Silver Spring, kindly mute.
Is it Silver Spring?
Yes, Shamak, we could mute them all.
Yeah. Okay. Thanks. Okay. So this is not balanced, and many of you will be very good at balancing equations. But in case you are not, this is what I teach my students. I write down all the elements in the equation underneath the arrow. I then write down the number of each one. So on this side, there is 1 Na. On that side, there is 1 Na. That's good. On this side, there are 2 hydrogens. On this side, there are 2 there, but there is another one there. So there are 3. So that is a problem. Oxygens, 1 here, 1 there. Because the hydrogens are wrong, I have to do something about it. So let's have some more hydrogens on this side. The only way to change the hydrogens on this side is to go 2 here. Now this is not 2. but 4, and the oxygens are now 2. So I'm now going to go over there and sort out the hydrogens, and I can do that by putting 2 here on the oxygens. So if I put 2 here, now on this side there are 2 sodiums. Now the hydrogens, there are 2 there and 2 there, that is 4. And the oxygens, there are now 2. The only thing left is the sodiums. So if I do that, I am now happy. So it is 2Na plus 2H2O goes to 2NOH and H2. That's how we balance equations. And they become more reactive down the group. As we saw, lithium moved around, sodium moved around more, potassium catch fire, cesium blew up, and then rubidium destroyed the experiment. Rubidium just exploded. Okay, let's just check that we've got this. Whoops. Sorry, just a moment. Let's go back. So here are the elements going in. This is cesium. This is cesium going in. But rubidium, being further down, that is a very violent reaction. It has destroyed the experiment. Okay, so that's group 1. Fairly simple, nice, simple stuff to see. So let's move on. So here we are. Here's our points about it. Group 1, they are good conductors of electricity. They are soft. We saw them cut. They are shiny when they are cut, but then they go dark and they float on water. Okay? Fairly straightforward. Conduct electricity. They are soft. They change when they are cut, when they are in the air. Excuse me. And they float on water. Now, the reason they are good conductors of electricity is because they are metallically bonded. I'm assuming you know what metallic bonding is. Can I just see thumbs up? Do you know metallic bonding? Is metallic bonding, the bonding in metals, is that okay? Dandora girls, okay? Wamuini, okay? Metallic bonding, electrons moving, yes, good. Glory, metallic bonding, excellent. Okay, good. I know you may be doing that just to shut me up. So the reasons, the reasons are these. So they are conductors of electricity because they have delocalized electrons. So in the answer, you need to say they have delocalized electrons, which can flow. They are soft. You don't need to say this only 1 delocalized electrons per atom. They are soft because they are big atoms and not very well attached to each other. Poor bonding. They are shiny because they are metals, but they tarnish because they react with the air. Okay, so they react with the air. Don't write everything down. It's just simple, and you will get this afterwards. And they float on water because they are not dense. Most metals will sink through water, but the group 1 don't. Okay? So that's the basis of group 1. Now you will get this presentation. So if your teacher wants to show you it or print out something, it will be there. Okay. So let's move on. So here we are with group 2. Oh, sorry, chemical properties. Sorry, my apologies. The chemical properties, physical properties are things like things which do not change the metal. So they do not react. Chemical properties are about reactions. The first thing is they are very reactive metals. They are the most reactive metals of their period. They get more reactive as you go down the group, and they react with water and oxygen and chlorine quite violently. Even lithium, if you get enough of it in a small amount of water, will catch fire. So the reasons, well, it's easy really. I mean, when we look at the electron arrangement, lithium is 2,1, sodium 2,8,1, potassium 2,8,8,1. They've all got only one electron to lose. So they're very reactive because they only have one electron to lose. They become more reactive as you go down the group because the electron is getting further and further away from the nucleus. So the nucleus cannot hold it very well. Okay, that's a very important idea. That because they get further, the electron gets further and further away from the nucleus. It means the nucleus cannot hold it, so it is easy to lose. And the reaction with water, we just did the equation, and it produces hydrogen. Sometimes they ask what you would see. And this is quite a difficult question. But what you can see, you can't say, I saw hydrogen, because we don't know what hydrogen looks like. But I can say it moved around, it floated, I saw bubbles, and the metal disappeared. I can say those. So let's move on and go to group 2. Can we go to group 2, Dandora? Cool. Okay, group 2. Now, don't write this down. I'm just going to tell you that your teachers, if you have a laboratory, should be able to demonstrate some of group 1 and some of group 2. And the best way to think about group 2 is that they are slightly less reactive and slightly stronger than group 1. So for instance, if we look at sodium, sodium is too weak to do anything, but magnesium is used in making the wheels for racing cars. Okay, so Na then Mg, Na too soft to make anything, magnesium stronger, group 2 stronger. And if we put them into water, sodium fizzes, reacts quite quickly. Magnesium does nothing. If we powder it, it goes very slowly, but most of the time, really nothing. Okay, so that most of the time, the best way to think about group 2 is that they are stronger, but less reactive. We're not going to go into them very much today. We will do something on them when we come to hard water and soft water. I'm just going to show you. I may show you. Let's see. Let's see if we can. Oh, no, it's not picking it up. My apologies. I can't show you that one at the moment. My apologies. So I'm going to just carry on with the original. If you, when you get this, your teacher will be able to show you that. Now let's look at group 7. Group 7 is, I've colored these the same as the colors were in the first periodic table. So we're going to have a look at group 7 and their chemistry. And you may have seen group 7. If you haven't seen group 7, it's quite an interesting group. Group 7 has been used as in many things, in medicines, in weapons, and so on. So let's just have a look at, where am I? Oh, where's it gone? Hang on. Not that one. Come on. Aha. So here are the halogens. And the first thing you need to know is the colors of them. The first one is very, very pale. So pale you can't really see its color. It's very pale green. Chlorine, they're all diatomic, so it's F2. Cl2 is yellow and quite dense. And the first two are gases. The third one, bromine, looks like a gas, but actually it's a liquid which evaporates very easily, and it is a like red-brown color. And the fourth one, iodine, is actually a solid, but it gives a purple vapor. So let's just have a look at them. So here they are. It might be worth writing that down. F2, green gas. Cl2, yellow gas. There's fluorine, it's almost colorless. This is bromine. Whoops, sorry, go back one. This is bromine, and in the bottom you can see it's a reddy brown liquid, but it is volatile. Volatile means it evaporates really easily. And then iodine is actually a solid, but when it warms up, it produces, you can see this very light purple color above it. It produces a purple vapor. Okay. So gas, liquid, solid. So fluorine, chlorine, bromine, iodine. Gas, liquid, solid, getting darker in color. Very pale green, yellow, red, and actually the solid for iodine is a gray, but it gives this purple color. Now what we're going to do is, sorry, go back just a moment. Okay, this is a tube with fluorine coming out of it, and this is some iron wool at the bottom, just iron wool. It is not heated. This is what fluorine does when it hits a chemical. It just burns it. Fluorine is so reactive, it makes things burn. Even charcoal. This is charcoal, like wood heated without oxygen. This is hydrogen in a balloon, and fluorine is going to come through here. Let's look at that slower. The fluorine bursts the balloon, and it all catches fire. Okay? So that fluorine is the most reactive. Oh, this is hydrogen burning in chlorine. So this is a tube of hydrogen caught fire, and it is being put down into chlorine, and it changes the color of its flame, but it is basically just burning in the same way as it does in oxygen. Okay? There are many, many experiments we can do showing the reactivity of the halogens. There is another one here. Excuse me. Don't worry about that one. It's not very interesting. Here is some aluminium powder and a gas jar of fluorine. Throw it in and it just catches fire straight away. Here is some aluminium in chlorine. It's not so quick, but it still burns really pretty well. Here's aluminium in bromine. There's some bromine. There's a piece of aluminium, and it takes a little while for it to react. But when it reacts quite violently. It just takes a moment to get it to react. There it is starting to react. But what all these do is to show that fluorine is the most reactive, then chlorine, then bromine, then iodine. Okay. Excuse me. So the things that we need to know. Let's go back to the screen. Here we are. So the first thing is the physical properties. So they have low melting and boiling points, and it goes gas, gas, liquid, solid. Try to remember fluorine, gas, chlorine, gas, bromine, liquid, and iodine, a solid. They have the sort of smell which you may remember. You may know the smell. For instance, in swimming pools which have been where they have killed the bugs with chlorine, you know that smell. And they have colors, and you need to know these. So here they are. The low melting point and boiling point is because the F2s or the Cl2s or the Br2s are not well attached to the next ones. The van der Waals forces between them are very weak. The smells we know, bromine, the name actually comes from bromos, which is for stench, which means terrible smell. And the colors, pale green, yellow, red, brown, grey solid. Whoops, I've misspelt witch. That's terrible. Violet, purple vapor. Chemical properties, chemical, so gas, gas, liquid, solid, pale green, yellow, red, purple. Chemical properties, they are very reactive. The most reactive is at the top of the group. They react easily with metals. And the last thing is important because you need to know a use of them, and that is that they react with water to form bleach. Okay, they react with water to form bleach. So the reason they are very reactive is because they only need to gain one electron. It is easier to gain one electron if you are a small atom, because you can get near to something with your nucleus and pull the electron from them. So there's only one electron to be taken. Small atoms are good at that. So fluorine is more reactive than chlorine, which is more reactive than bromine, and so on. The opposite of group 1. They react very easily with metals. Here's an example. 2Na plus Cl2 goes to 2NaCl. Very simple. Don't worry about the bottom equation. Just remember that they react with water to form bleach. Okay. And finally, we are on to the noble gases. Now, the noble gases are peculiar, and they only have 2 properties. And here are their physical and chemical properties. The physical property is that they are just gases. They are colorless, they are odorless, we cannot smell them, and they are gases. They are highly unreactive. In other words, they are very unreactive. They do not react. It's not quite true that they do not ever react, but they do not react unless it is fairly extreme conditions. So xenon will react with fluorine if it is heated, but most of the time they don't react. And the reasons? Well, the reasons they are gases is that they are monatomic. In other words, they are single atoms, and there is almost no force of attraction between them. The van der Waals are very weak, which means they just spread out. They have very, very low melting point, boiling point. They're all gases. The reason they are very unreactive is they have full outermost shells. You probably know this. They have full outermost shells. That means they can be used in many different places where we need something which doesn't react. So they are in some light bulbs. They are sometimes in welding for sticking metal together where we do not want oxygen because otherwise it catches fire. They can even be in foods because the foods do not want oxygen because otherwise they can go bad. Okay. So let's just go back. to this question. So here's a question. Here's the question. Now, this is the one I said we would be able to do. So let's look at the compound formed between C and A. Have a go at this. What will the formula be between C and A? Remember, this will be group 1, group 2, and the last one is group 8 or 0, so A is in group 7. So try and work out what the formula is for C and A joined together. Come on, Glory, have a go. Glory. 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 Hello, Glory. Pay attention just for a moment. I have a question to ask. Glory, is this all really, really easy for you? Glory. Glory? Please pay attention just for a moment. Is this all really, really easy for you? Glory. It is really easy. You can do it all. You know it all already. Is that right? Okay. So let me tell you, the way to succeed in life is to know when to really take what is being given to you as an advantage. And one of the things you need to do is to really try to do well in examinations. They are really boring. Examinations are boring. And they are something that none of us want to do. But if you can do them and you can do well, you will change your life. Glory, try changing your life. Right. Formula between C and A. Which element has the same electron arrangement as the stable ion of F and A? So F is in here, which is in group 1. So when it reacts, F will lose 1 electron and be 2,8. So which one will be the same as F1 plus? A is in group 7, so it will gain 1. Because it's up here at the top, it is number 27, and therefore it will go to 2,8 and become A minus. So which one here, A minus, which of the elements here will have the same electron arrangement as A minus? So if it goes from 2,7 to 2,8, which one is the same? Element Q is number 15. Where is it on the grid? Well, we have to remember that hydrogen is up here on its own. So that's 1, 2, 3, 4. Now, this is a bit naughty because this should be labeled as transition metals. If you go 1, 2, 3, 4, 5, 6, 7, 8, 9, that one there, column 3, should be the transition metals. So 1, 2, 3, 4, miss that one, 5, 6, 7, 8, 9, 10, 11, 12, miss that one, 13, 14, 15. It will be here, next to G. Now, we're going to do this thing about atomic radius and so on, but let me just give you the answers. C and A will form simply Ca, because C is in group 1, valency 1, A is in group 7, valency 1, 1 and 1. Which element has the same as the stable ion? Well, F plus will be 2,8 and E is 2,8. And A picking up 1 electron will be A minus, and that's the same as B. Okay? So now we're going to, 15 we did, 15 comes in here. Okay, now we're going to look at atomic radii and so on. So, gosh, we've done all this already. Wow. Okay. So now we're going to look a little bit, just for sort of 5 minutes, we're going to just look at the periodic properties of the period Na to Ar. Firstly, I want to just show you something which is quite useful. Sometimes they do not give you the periodic table. If they don't give you the periodic table, you need to know something about the sodium period. Let me show you an easy way to remember it. This is the period. All you do is you turn it into a stupid word. Glory. All you do is you turn it into a word. So you just read it like it's a word. And the word is Namgal-Sipsklar. Now that sounds pretty stupid. It's not like it doesn't mean anything, but Namgal-Sipsklar is the way that you can remember all that. Namgal-Sipsklar. You look at it, N-A-M-G, just join the letters together. N-A-M-G-A-L-S-I-P. Namgal-Sipsklar helps you remember all those elements in order. That is useful because if you're not sure what the fourth element is, Namgal-Sipsklar, silicon. Okay, so Namgal-Sipsklar, pretty stupid word, but it helps. When at the beginning I wrote all those elements together, that's because they all make stupid words. The whole periodic table you can remember by making stupid words. And it helps because you can be confident if you can remember this stupid word, Namgal-Sipsklar, Namgal-Sipsklar, Namgal-Sipsklar. Try saying it to yourself, Namgal-Sipsklar. You've got it. That's the period. Okay, so let's go and have a look at something to do with the period. Here it is. Okay. Firstly, the elements, there it is, Namgal-Sipsklar. Okay, Namgal-Sipsklar. There they are. Okay, Namgal-Sipsklar. Here they are with, don't write this down. You can work this out yourself. There's no point in writing it down. What I want you just to remember is this, that there is a break after 3 and then after 4. Okay, and the reason for that is it goes sodium, metal, magnesium, metal, aluminium, metal. Silicon is a metalloid. After that, they are all non-metals. So metal, 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 metalloid, non-metals. Lose 1 electron, lose 2 electrons, lose 3 electrons, share electrons, gain 3, 2, 1. Metal, 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 metalloid, non-metal. Okay, really simple, really nice and easy. Okay, now there are a whole load of things which you need to know in the trends. So I'm going to just look at one now. We'll do the rest next time. This is a slightly surprising graph, and we'll talk about why it happens. Whoops. There we are. Atomic radius across period 3. And what it shows you is that sodium is the biggest of the period. Now that might seem peculiar. That might seem weird because sodium is the one with the least number of protons the least number of electrons, the least number of neutrons. Okay, sodium has 11 protons, 11 electrons, 12 protons. When you go to magnesium, suddenly it has another proton and another electron, but it's smaller. Look at the graph, it's smaller. So sodium, 11 protons, magnesium, 12, aluminium, 13. And look what's happening. They're getting smaller, but the change is getting less. So from sodium to magnesium, big change. From magnesium to aluminium, big change, but a bit smaller. Aluminium to silicon, smaller. So why is this happening? Can anybody tell me why this is happening? Can anybody unmute and tell me why that is happening? So as we go across the period, the atoms get smaller. You would think they get bigger. Why do they get smaller? Anybody got any idea? Somebody must have an idea. We only have like 2 minutes. Somebody must have an idea. Okay. Here. Sodium is 281. Magnesium is 282, and so on. And it is this which is important. They are all going into the same shell. So here is sodium. Sodium has 1, 2, 2, 8, 1. In the middle, it has 11 protons. Okay? So its atomic radius is from the nucleus to the outermost electron. Magnesium has another electron in the outermost shell. So I put another electron in the outermost shell. But it has 12 protons. Because it has 12 protons, that is almost a 10% increase. More protons pull harder. So now this shell is not here, but it will come in a bit. The electrons will be pulled in more. By the time we get to chlorine, although it has 7 electrons in the outermost shell, it has 17 protons. So the reason that the atoms get smaller as you go across a period is that in any one period, the electrons, the outermost electrons, are going into the same shell. But as we get more and more protons, sodium, 11 protons, magnesium, 12, aluminium, 13, 14, 15, 16, 17, 18. And then we get a new shell for potassium. So in any one row, in any one period, the electrons should all be going into the same area, same volume, same size shell, but that shell is pulled in by more and more protons. That's it, guys. That's the end. Okay. So, okay, I'm going to stop recording now.